Hello. 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 Get an echo. Yeah. So last week I wasn't able to get the music playing in the background, so if anyone's there and can hear the music in the background, please let me know. That way I can know for sure that the music should be playing. Just figure out my settings. Alright, everything was good. I did test it out earlier, so I think the music should be playing. Yeah. So today we're just gonna be doing a chill stream, working some more on the LRUCache we built last week, or started last week. Starting with the linked list. So right now, so last week I was kind of getting too stuck on the linked list because I was kind of, okay, a linked list needs this method, needs this method, needs this method. But in reality, like if we're building our LRUCache, the linked list that's going to be backing our LRUCache only needs like a small subset of the actual function, like the methods. So the methods that we're probably going to need is, whenever you set something or add something to your LRUCache, we want to essentially add that thing to our linked list. So we're going to push it to the front. And then if the cache has too many things, then we need to remove something from the cache. So we're going to need a remove method. And then whenever we add something to the cache, or whenever we fetch something from our cache, we need to move that item that we fetched to the front of the cache. So that way, or the front of our linked list. So that way we know that's the most recently used thing. So yeah, actually no, also we need, I think we might need like head method to get the head node, and then the back method, or tail method to get the tail node. And then, let's see, I had this remove one be like a kind of a generic remove node, but I think I think we'll keep the remove method there, and we'll have a tail. All right. So that looks okay for now. So I have a new method, I have my length method, I have my push front. Oh, awesome, thanks. And so you're able to hear the music, right? So yeah, last week the music wasn't working, but I think the music should be working now. Oh, cool. I'm glad it works now though. Okay, cool. So I got, awesome, thanks Justin. So we got length to get the length of our linked list. We got push fronts. I'm still working on this, so let's make a little note to make sure that to finish this method. All right, let's finish that one. What else? We got gets like to fetch a node at a certain position. We might not need this for the LRUCache, but we'll keep it for now. And I have this little kind of helper method to like get the node of our because our linked list is basically a series of nodes, and this little helper method gets a node at a certain position. So we have that. So I think this right now I'm just gonna get rid of the error because I changed it so that before I had it so this method was returning an error. So you're gonna see a lot of places where it checks to see if there's an error still. I think I might got rid of most of them, but now I have it in panic instead because I didn't like the kind of messiness of having to return an error for some methods but not others. So I want to try and keep the interface a little more clean and never return errors. But if you have, for example, if you try and fetch a node that's not at the correct position or is like out of position, I'm going to return a panic instead. Because it's kind of similar to if you're trying to fetch an item in an array and the item is out of bounds. It's kind of similar where like the program is going to panic instead. So I'm going to try and have that same kind of behavior. So I think get is working. All right, so let's try and work on this push method. So this push front, essentially, I'm going to push a value to the front of the linked list. So the value is going to be kind of a generic interface. So it can be any value. It can be an integer, string. And I want to essentially create a node and then add that to the front of the linked list and kind of push everything else down. So what we have here is I have a kind of defer function. So when this function returns, it's always going to increment the length, because assuming that this function is successful, which it should always be, we should always return the length, or it should increase the length. And then if the length is 0, meaning that we have an empty list, then what we're going to do is we're going to set, instead of creating a new node and kind of pushing every node back, we're actually going to set the root node as this value. Because right now, if the length is 0, then essentially our list is empty. So we need to have we need to set the root as a value, a certain value. So actually, I'm going to return the root in this case. All right. And then if the root is not empty, or if the linked list is not empty, then we're gonna basically have to create a new node and put it at the front. So let's do that. So let's kind of write it a little bit. So if list not empty, we're going to create a new node and put at front. What this means is we also have to make sure that the new node's next value is the current root node. So new node next value equals the current root, and then the previous value, so the new node's previous value is going to equal the tail. So it should be the current root's tail value. If that makes sense. Let's see. So yeah, so what we're gonna do, so I don't need this anymore. So we're gonna create this new node. So I have this new node, I'm just gonna move this up here. Create that here. So create a new node. The value is gonna be this value. So the next value is gonna be this, the current root. Because essentially this new node is gonna be the new root. So actually no, this should be the next value. So the next, so like it's the next node in line is gonna be the current root until we change the root value. And then previous, previous is going to be the root's previous, the current root's previous value. If that doesn't make a ton of sense, let me know. I can kind of explain how that works. Okay, so we have the new node. Next, what we're gonna do, so once we now have the new node pointing at the root, we need to make the current root's previous value. So the current root previous value is gonna equal the new node as well. So that way they're kind of pointing at each other, because this is a double linked list. So each node has a previous and next value. So the current node's previous value should be pointing to the new node we're creating. And then also the tail, okay, this is where it gets a little confusing, because the current root's previous value should equal new node. And then the tail, so the tail linked list should also now, the next value of that should point to the new node. So this is gonna be a little weird. So the previous, it's kind of funny. The root's previous value, which is the tail, the next value should now equal the new node. This looks really janky. I gotta make sure this. That looks super weird. It makes sense in my head, but yeah, okay. Let me just test this out, and that's what we have tests for. And then so what we're gonna do is then set the root to now be the new node. All right, so let's actually just test this. I feel like this is way too crazy. Yeah, so let's make some tests. All right, so we got test. Where are we at now? Test, okay. All right, we're gonna make some tests. This is a push front. So if you aren't familiar with Go has very kind of strict ways to do tests. You have to, the name of the file has to be like underscore test, and then the function of each test has to have test in the front. And it's kind of best practice to then, after test, put the name of the function that you're testing. So in this case, push front. And then it should always accept this like testing framework. This is kind of like a built-in testing library in Go. So now what do we want to test? We want to make sure that when the list is empty, push front should just set the root, should set the root value as the passing value. All right, and then when the list is not empty, push front creates a new node and sets it as a head value. And then we also kind of change the surrounding values. So let's do that. So yeah, so let's do that. So first thing first, we're gonna do trun, make it a nickname. So empty list. And then I think, yeah, we test the func. We're gonna pass in this testing library. So it's basically a callback. All right. I'm actually gonna make this. So then let's say that we're gonna create our list. So our list is gonna be empty list. So it's gonna be just list.new, which is gonna be empty list. And one thing we have to make sure is that we're not using the built-in Go list library. We should be using our library, which should be this cache go list. There we go. So that is our library. New. What else? So this is gonna be empty. So this is gonna be the empty list. So then when we do, we're gonna do l.pushFront of just a random value. So let's say the value is gonna be 5 in this case, just a random value. 5. Push front. Oh, one other thing we should do when we do push front, we should actually return here. We should return the node, which I don't think I'm doing here. Yeah, so I'm not doing that. So I'm gonna be doing new node. So we should actually be returning this node that we create. That will help with testing and also helps with actually using the library. So we're gonna do node equals push front. All right, so we got node, and then now what we wanna do is assert equal t, and then so the node's value, one thing we should do actually is create, let's make this an exported value. So that way, when people use it, we can actually retrieve the value. So we're gonna do value, and then we're gonna, since it's coming back as an interface, meaning like it's coming back as a blank generic value, we want to cast that into an integer because we know it's already an integer here because we're passing it as a 5. And so that should then equal so the value, so basically saying that this value should equal the node that we get back when we do push fronts. So let's, oh, I didn't do, all right, one thing I need to do is go get. I haven't done go get yet, so let me just copy this library because I haven't actually installed the assert package in my computer, so let's do that. Also, before we do that, let's go ahead and tmux, it'll be a lot easier. There we go. So go get, and then that one. So now we're gonna get that package. How's everyone's day going so far while this loads? All right, that works. So let's go list. All right. One thing I should do too, actually, is I should create like a makefile. I should test. Go test. And then we should probably do one. That should probably be fine. Ooh, what's wrong? Import cycle not allowed in test? What's wrong? That seems strange. Oh, what it is actually don't need this because we already are. Oh, okay, sorry, I'm dumb. We don't actually declare list here because we're already in the list package. So all we need to do is new. There we go. Let's try again. And now I've broken my code since I made this an exported field. So let's try that again. Alright, the first thing we're gonna do is we're actually just build this package and get the compile errors. So yes, so here there should be value. We're actually gonna do that. We're just gonna do where are the other lowercase values. Change that. That's change. All right, now it's fine. So let's do doubly again. Yeah. Unnode field. I think I already fixed that. There we go. Okay. Now. Go see this. All right. So it indeed does work for empty case. Alright, so this is in case it does in fact work. So if we push front 5, the node we get back does have 5. But one other thing we should do also is make sure that. Because I don't think actually that doesn't really test it so much. What we actually want to do is like try and retrieve the first value, which case is so if we do get 0, we should be getting the root node, or we actually just do head. Let's just do that. That'll make it a little easier. So we can just create like a helper function, basically just get head, which will return the head node. And then so basically return l.root with the root node. And similar for this, we're gonna do a tail. And then for this is going to be previous because doubly list refers to tail. All right. Because Go makes you make comments for everything, we're going to do head returns the head node of the list. And then tail returns the tail node of the list. Cool. So what we're gonna do now is, if we do asserts equal t, so the expected value is gonna be val, and so we're gonna do list head and then value. Actually, we're gonna and then also cast that as the integer. So that should also equal or be equal. Yep, okay, cool. So empty case list works. Now let's try it where the list is not empty. Non-empty list. So first what we're gonna do is we're gonna actually push 2 things. So I don't actually care for this return value. I'm just not gonna care, but now we are going to do wave second value. Let's do 6. Actually, let's mix it a little bit. Let's actually do a string. That way we can make sure that we're doing different, not just integers all the time. All right, so we're gonna push 5 there. Then we're gonna push a new node, which is foobar. And so foobar should now be the return value. So actually, let me make foobar a variable so I can make it a little easier. All right. So pushing it twice, and now what I want is the node that comes back should be foobar. And then head value should also be. So the other thing here is that since we're pushing two things, I also want to test the tail is actually 5. I want to make sure that everything kind of works properly. So what we're going to do here is, I might just copy this. So what we're going to do here is make sure that this is 5. And then we're actually going to get tail. And we're going to cast that as an integer. So this should also work, or ideally should work. Ooh, here we go, we got some segment faults. So what line is it at? Alright, so line 30? What's happening on 30? Okay, so tail apparently, okay, so apparently tail is not returning. Let me do some really sophisticated debugging. What does tail work here? What does this equal? Is it pretty bad at it? What's happening? Oh, I think it's this. This is probably where. Maybe let's try it one more time. Super sophisticated bugging. Debug. Alright, now let's test it again. Huh. 3, 2. Tail, is that? Interesting. It's saying this is a seg fault, meaning there's not tail? I thought I had a tail method. Let's do some more debugging. Do I have it? Okay, I set L as that. Okay. I have tail method, which should be fine. Now I'm gonna do. Let's try that. Oh, here's all the things. Okay. So we are getting debug. Now I gotta change it because now I'm not sure which debug is where. Let's do debug 1 and debug 2. There is better ways to debug in Go. There's like a package called Delve, which is like helps you kind of create breakpoints, similar to how JavaScript has in the terminal or in the browser. But I'm not super good at it yet. It's a little there's a little bit of a learning curve to it, so I haven't really learned that. So I'm kind of go to console outputs. That's my go-to debugging. All right. So debug 1, meaning so, and then debug 2. Bar. Oh, I think I have the issue. Oh, okay, I know what it is. I forgot. When we initialize new, so when we initialize new, yeah, okay, that's what it is. So I'm setting a blank node for root, but what we actually need to do is, I think what we need to do is basically, so root is going to be a new node. And then what we're going to do is it's going to be a empty node, but we're going to set next with the root, and then previous equals a root. Because right now, our previous value is just a nil value. So if we try and do, oh, what's happening? Because, oh, I need to come over there. So what's happening is when I do tail, I'm calling root.previous, but root.previous is a nil value. So when I try and do tail value here, it's getting a seg fault because you can't call value on a nil value, on a nil. So what I need to do is actually set the previous and the next of the root value when I initialize it as the root value, as the root node. And then that will change as we go along. So when we push front, so that's okay, let's go through a case where it's not empty. So we're gonna push a value to the linked lists, and then the root is gonna be whatever we pushed previously, so in this case 5. And then with our test, we're setting a second, we're calling foobar at another time with this string. And so what that's gonna do is it's gonna create a new node where the next value is the current root, because we're pushing the root back, so it's gonna be, or we're pushing the root to the side. So the current, the new root is gonna be the old root essentially. And then the previous value is gonna be root previous. Is that working? Does that make sense? It does make sense because it's pointing to itself. So that should work. Now, this new root previous should be, so the old root's previous is gonna be the new node. And then, oh no, we can't do this though, because if we assign previous as new node, this is just gonna be the same thing as this, because we're doing that. Okay, so what we need to do instead, no, I think, okay. So we're creating a new node. It's going, actually I need to draw this out. Maybe just draw this out, maybe a little more sense. Come on, paintbrush, okay. No check. Okay. This over here. All right, so we create a new node, we create a road. Actually, it's like over here. So we go in the middle. So this is the first node we create. It's gonna be value 5. And then that is essentially pointing to itself. So its next and its previous values are pointing to itself. But then when we create a new node, let's just call this foo. We want to make this, the next value of this. We want this previous value to now be this. And then we want this is next value to also, the tails next value to be that. Okay, so what we need to do in this case is, I think what we need to do is to initialize the value of the tail, because that's going to be the, oops. Okay, and then, oh, okay, yeah, I think so. The music that's playing is like a pretzel app that I have, and so the reason why I'm using it is because it uses like I think non-copyrighted music, because Twitch has like a DMCA rule where if you play copyrighted music, your stream can get taken down. So this app plays like non-copyrighted music. But whenever it changes songs, it posts a new update in the chat saying what song is playing. That's kind of like that's kind of like a compromise you have to make by using it. So that's probably why you're not seeing some of the chat messages, because it's just basically the app is called Pretzel, and so it's just posting in the chat saying what song is playing now. So that's probably what you're missing, is just the song name, but it doesn't really matter. It's not really an ad, but if you're interested in it, it's called Pretzel. All right, but yeah, so basically, in case you missed it, we're basically I changed up the linked lists API. So with the LRUCache, there's only a subset of commands that you really need for linked lists. So right now I have push front. So basically I can just push a value to the front of the linked list. I can remove a node. I can move a node to the front of the list. With the cache, whenever you retrieve a value, you want to set to the front of the linked list, because it's now it's the most recently used. So we want to set to the front. And we have some helper methods to get the head and the tail of it. So right now I'm just working on push front. So right now I created some tests and I'm trying to debug those tests essentially. All right, so tail, I'm gonna create like basically a temporary value of tail, which is gonna be previous. So now the tails, all right, and so then we go back here. The tail's next value should now be equal to the new node. And then also the current root's previous so the current root's previous value should now equal to new node 2. Because that's what this is. So this is the current root. I'm saying the previous to equal foo. And then foo's next equals the current root here. Its previous equals the root's previous, which is itself, which makes sense too, because I'm going to the tail. And then, yeah, I think that should help. I mean, we have tests to help make sure that. But let's try this out now. Man, linked lists are always confusing to me. I always have to drop them out. So we still have a seg fault. What is happening? Let's get rid of this. I wish there's a way like visualizing the commands as they come through. I mean, I could just do like print statements. So root previous, and so I set the new nodes. The new nodes previous should be that. So where is the seg fault happening? Testing 33. Oh, here we go. And so this is a little bit different actually. Interface conversion. Interface is nil, not int. Interesting. So this is a different error than we got before. So what it's saying is that the tail that we get back, when we try and convert it to an int, that doesn't work because it's a nil value, which shouldn't be right because the tail should be the old root, which has a value of 5. So let's do some more of this super advanced debugging. Debug statement. And so what we're going to do here, tail, and then we're just going to do value. Debug. So there's a nil. So the tail's value is nil, which I still don't understand. It has to be something here. So what we're doing, setting the value to value, and then the next value. So let's make this bigger, and then we just have half screen. So we create this new data. The next value is going to be the old root. This is the old root, and the previous of this, which is going to be here, is this current root's previous is still itself, so we have it up here. So in other words, I'm setting it to this previous, and then tail. So this root's previous, which is itself. Yeah, so this is essentially a tail. So this is the tail. I'm saying that the tail next is going to be new node. Yep. And then the current root's previous, which is this, should now be new node, which all looks right to me. Why is it? It seems like for some reason that's new value. With a new node, and then next and previous are boast itself. Alright, what else is going on here? Well, let's just do one thing first. So we're just gonna make sure that this works. So that way, just gonna make sure that this first works. Alright, so these all work. So it's basically getting the tail that for some reason is causing an issue. Tail value. Alright. So it has to be something around here. And so instead of doing tail, let's just do this. I'll put what the tail value is. So it does have a previous value. I believe it's its previous value. Oh wait, so I think it has. Okay, so it has a previous. It has a next value. Interesting. So right here, previous is nil, but next is not. So I do this. The root's previous, so this current root's previous, which is self. The tail. Tail at next is new node. So for some reason this oh wait. Okay, I think it's basically because I'm setting oh wait, no. Let's see. Something has to do here. Basically it has to do something with here. So current root, previous is gonna be tail. Tail is current root's previous. Let's go from the beginning. Alright, so it's 5. And then so tail is gonna be, and then so list currently refers to itself as both next and previous. So the tail, this is gonna be equal to tail. So then tail.next, so this is gonna be equaling the new node that we have in here. And then I think it has to do something with this. So what we're saying here is that this root's previous is not going to be this node. If that makes sense to me. The difference between... Oh yeah, good question. So this right here, so if you do colon equals, is basically a quick declaration. So instead of having to do like var tail node and then equals, you know, this, when you do this, so when you do this instead, basically the compiler is gonna at compile time is going to basically interpret what the type is, because normally, because with Go is a type language, you have to set a type. But by doing this, what I'm doing is I'm gonna let the compiler check with, or basically define the type at compile time. And so you have to do that when you first create a variable. So I haven't created tail yet. This is the first time I'm referencing tail. But then once I've created tail, in the future I can do tail.equals and then do like nodes like that. So it's when you first create a variable, you have to do this like colon equals. But if you've already created it, you can just do equals. It's kind of similar with JavaScript when you have to do like let or const when you first create it, then afterwards you just do equals. It's a similar idea. All right. Yeah, this thing is confusing the heck out of me. I'm gonna actually cheat a little bit. I'm gonna cheat a little bit. What I'm gonna do is I'm actually going to what I'm gonna do is I'm gonna import. So Go has a built-in doubly linked list package called list. So, and what I'm just gonna do is basically just call this just do list.new. What this allows me to do is now I can kind of go to the definition of this. So with Go, the nice thing about it is I can actually go to the definition of a method. So I go in here as Go. If I do like a little go to definition, it'll actually bring me to the definition of this language. So what I'm going to do is I'm going to cheat a little bit and see how they do it in their own thing. So let's lazy-knit. So let's see what new was. New list, and their list is defined as what? Root is an element. Oh, interesting. So their root is actually not a pointer to an element. It's a value of. It's like just a copy of. Interesting. Okay. All right, and then all right, so they're just doing that, which is, I think it's kind of similar to what I'm doing here. So the root is an element, and then all right, so it's similar to what I'm doing here, where I'm doing this. When I do new. Where's my new method? Here, I'm doing basically a new node. I'm setting root and previous to be that. Interesting. Maybe I could try something else. What if I do this? And then it's going to be point of that. So I'm curious if that's part of the reason why it's not working. I'll have to double check later. But also let's do this. I just want to see how their push front method works. So mine's not currently working. So this just initializes it. This is insert value. It's going to push value at the front. So what this does is it creates an element and inserts it at the root. So this does element previous equals that, element next equals at next. Interesting. So what it's saying is that, so let's draw this out. I'm curious how they do theirs. So what they're saying is that, so this method in the actual Go language saying that this element, that this node that they're putting in is going to be inserted at this other element, is their own way of defining it. Basically, they're putting this element at the root. So at here is the root. So what they're saying is that e previous, so this is going to be the new value, and for this is going to be foo. So So previous of that is going to be the root, which makes sense. Wait, what? Which front? So they're saying this previous is going to equal the root, which doesn't make sense to me, but we'll look out. So this is going to be the root. This next is going to be the roots next. So in this case, whatever the root was referring to before, which was the root. And then E previous next. This is confusing to me. So E previous next. Oh, this, which is this. Okay, this is equal E. And E next previous is going to be equal to E. But they're not inserting it in the front then. It's not the root value anymore. Oh, wait. Oh, I think I see what they're doing. Oh, interesting. So what they do, oh, this is interesting. So what they do actually is they don't even, so basically what their list looks like is they have this root node, they have this l.root, and this is basically an empty node. There's never a value for it. But they use this as basically the boundary of their linked list. So they have this root at both the front and the rear. And so the actual linked list is like everything between. So in this case, our foobar would be here. The 5 would be here. And so they have like pointers here. So basically the actual linked list is here. And they have this like empty root node, essentially the boundary. So if you know that, like, for example, if you iterate over this linked list, once you get this empty root node, you know you're at the end, and then vice versa. Oh, interesting. Huh, I didn't realize I did that. I might want to steal that because it's definitely getting a little confusing with this way. So let's, let's see if it's too much work to try and do that. So in this case, what we're gonna do is have previous next, which is what same. It's the same thing here. And so then L.length equals 0. Because it kind of makes sense, because you kind of want to have those nil boundaries to know when you're at the front at the beginning. Oh, it's so interesting. Very interesting. Okay, so that's new. For us, it's gonna be new. Length is the same. This is the same. So instead of doing this though, so what we had here was basically we're creating a value at the root. What we're gonna do is we're gonna create this new node. Let me get rid of some of these things. We're gonna create this new node. And then so next, so we're gonna say is previous is actually the root. And then the next value is actually the root's next. Oh, what happened? That was weird. What am I doing? So then the root's next value, so the current node's next value is going to be the root's next value. Oh, I actually have to do this. Okay. You have to do this because of the pointer to the root. Oh, nope. Oh, I think we have to do. Unfortunately, I think this is a little weird syntax, but basically, we have to reference the pointer of the root, and then do dot next. I think we have to do that. We might not have to. Basically, what's happening here is if I don't reference the pointer of the root, it's just going to get the value of the root and do next. So I think this is actually fine. I think I can actually just do this. And then basically now what we do, we have to say the root next is going to be equal to the new node. So this root next equals the new node, and then I think root previous. What's the root previous? Was going to be the root previous is going to be basically this. So I think actually the way that this root, the way that they implement their linked list actually kind of looks like this. I never figured out how to empty this whole thing. How do you, all right, we're just gonna start doing what the built-in doubly linked list look like. Actually, so they have this kind of root node at the top, and then it kind of goes in a circle actually. So it basically kind of goes like this. So they have a node over here, node over here. Like when they build out your doubly linked list, this is kind of what theirs looks like. And so this root, so when we add this value, this they even need to change. What do they do with theirs? Where's their push front? Yep. Okay. Insert. So yeah, they're passing the root, pointing to the root, passing the value. What they're doing now is they're creating an element with this value in there, and they're inserting it. And so what they're doing now is so then their new value here, previous, is going to be the root. Then their next value is going to be at next, which makes sense because it'll be this. And then previous next is going to be this. Okay, so then, and then I got that, and then next. Oh, what is it? So you're doing the okay, so that's what we have to do. We basically have to say the oh, gotcha. Okay, so what we have to say now is we're basically going to do node next previous is going to be new node. So what that means is this value, this is the new node. Its next value over here, we're setting the previous as the new node. So that's what this means. So new node next previous equals a new node. Yeah, like this. But we're not going to set the root because the root is always going to be this empty kind of default empty one. Okay. So let's see if that works for us. So we're definitely changing things up a bit because we're kind of do the same thing where we have this empty root node, but I think it's going to help us out. So this head actually is going to do next. Oops. Oh, come on. What do I do? Next and previous. Okay, there we go. I don't think we'll be using this as much, but we'll see. It's a push front. All right, now let's actually check these. Let's check this. So we have this still. Does that all make sense, or is that a lot confusing? I try to draw it out to make it look more sense to me, to you, and also to me, because I need to draw it out. But yeah, let me know if it's super confusing. All right, so now what we're gonna do is test that out. All right, so cannot use. Okay, so we have to reference the pointer. So saying we can't use typical node when we define it as a pointer of a node. So where was that at? Line 109. Oh, okay, this is it. I'm just gonna comment out this method for now because I'm not totally sure if I'm gonna need this super that well. And same with this. We might need it later, but I just want to copy it out so we're not getting those build errors. It was, oh, this is okay. This is the. Alright, let's try it. Whoa, alright, it worked. Alright, cool. So cheating a little bit and looking at how Go's native language actually did it, it worked. Alright, it makes me pretty happy actually. I mean, we weren't necessarily able to figure out completely on our own, but we did, you know, look at the source code and see how they're doing it. So that should actually help us with the next couple stuff. So we have, we did push front. That is working. I don't know how to make a check mark. We'll just do X. We did head, and now tail. We did that. Okay, now we're gonna do remove. So that should be a little easier, hopefully. All right, so remove, what we're gonna do, so since that push front actually like returns the nodes of the linked list, what we're gonna do is we're gonna allow someone to pass in one of the nodes and we're gonna remove it from the list. And so let's try and so let's move this out of the commented out blocks. All right, now we're moving it a little bit. All right, so remove is going to remove a node from the linked list. Cool. All right. Move. It's gonna be node. It's gonna be pointer to node, I think. And then should I return? We just boolean to say if it returned or not. So when we remove a node, all right, that's close enough. So when we remove a node, what we want to do essentially, so let's say that it was this node here. This is our doubly linked list. We want to remove this node. What we need to do, so each node is doubly referencing each other, so like this. So boom, like that, and then like that. What we want to do is we want to basically sever these ties. So we're gonna make this, the root, point at the next value, the next previous value point at current previous value, and then basically sever all these ties that it no longer references anything. So what we want to do in that case is, so we want to make the next node's previous value equal to the removing node's previous value. So let's do node next previous equal node previous. Same for the opposite, where we do previous next equals node next. All right, and then so that removes next previous. That removes this one. And then what we want to do is the current node's next, and the current node's previous is going to be nil. So that way we sever those ties. All right. And then return, not true. I guess we never really actually returned false. I guess we don't need to return anything in that case because it's always going to work because there's not really any case where an error can happen. So we're just going to do that. So yeah, so that should be fine. Let's yeah, let's try that. So what we do, we can make it a test case for that. On the test remove. All right, run node. And then essentially what we're gonna do is we're gonna create a node. So we'll create a list, basically. And then what we're gonna do is push front. So we're gonna create foo. And so this is gonna return node. And then what we're going to do is we're going to do the remove. Oh, one other thing we have to do actually is length decrease. So that way we know the length decreased. So we're going to remove this node. And then we should assert we're going to assert length actually. T object is going to be, oh wait, no, we can't do that. Equal T, I'm going to do length. And this should be 0. We call this. And then also one thing we should do here, I saw that one thing I saw that they did in the native list is if this length equals 0, so basically if the list is empty, we should return nil here for the node. Because what this is going to do is there actually, when we initiate this, there actually is an empty root node when we initialize it. So instead of returning the empty root node, we're just going to turn nil. So same thing here. And the nice thing about that is now we can actually use that for our testing. So we're going to do assert nil, and then we're going to do head. R should be T. All right, so we're done. So we're going to start this as length 0, and then the head value is nil. So let's do that. Perfect. So I did a success. To do a double check and do a test. Cool. All right. So where are we at? Oh, that's the wrong one. So you got this. All right, so you got remove. All right, now we should do move front. So when we move something to the front, let's just get rid of all these. I really gotta figure out how to completely empty out this paintbrush app, or like make a blank slate without just creating a new one. All right, so we move something to the front. So we have this root node. Let's say that it's pointing to this node over here, and it's pointing to this over here. So let's say we want to move this node to the front being this one right here. So this is F. What we want to do is basically have the roots next equal this. So we're gonna have this point to here, this previous point to here. So that should be easy. But the next thing we want to do is have the current front previous point to this. So this is gonna be previous. And then this one's next point to the current front. All right, and then we can get rid of that. And this. Okay, so let's try that. Move front. It's going to move the past node to the front. List. All right. Move front. All right, and then all right, cool. So then what should happen is I'm gonna create create a temporary called current front, and that is gonna be what is it? It's LRUCache.next. It's the current front. So then what we're going to do is the node that we're passing in, we want the previous of this should be the roots. We're doing a pointer because the previous should always be a pointer to a node. That's why we're doing this notation. And then root.next should be the node. So now what we want is the current front. So this is the current front. The next value of this, so current front next is going to be the node. And then previous, there we go. And then node next, sorry, current front. All right, so that one should be, that should make that happen. Let's make some tests for this. Okay, test move front. Test and T. So what we're going to do is run this test. It's going to be move node to front. Func. All right, and then what we're going to do is we're going to push something on. So make a new list. And then what we're going to do is we're going to push front something. So pushing the front. Say it's 5 again. And then we're going to push something else in the front. Let's do this be foobar again. Let's make foobar a variable so we can use it for asserting. All right, about 4 bar. All right, so we're gonna push that to front. We're getting a node back from that when we push front. So what we're gonna do before we actually do the move front thing, we want to do some assertions to make sure that the current state is how it is. So we're gonna do assert equal, and we're gonna do oh, we should actually need, let's do node 1, node 2, because that's sophisticated. We're gonna say node 1 should be what is returned when we do head, node head, because it's the current head right now. But then once we do move front and we do node 2, what should now happen is when we do assert equal on the head method, node 2, this should now be the front. That should now be the head node. So let's double check this. Test. Ooh. What happened here? Expected actual was foobar. What happened? Oh, push front. Oh, never mind. Oh, actually, so yeah. So I forgot, when we push front, we actually push it to the front. So what should actually happen is this should be, so you're actually not gonna need foobar. So because we're pushing foobar to the front, then foobar should be at the head, but then once we move node 1 to the front, back to the front, then the front should be node 1. Let's try that. There we go. Okay. Perfect. So I think that's good enough for now in terms of our linked list, because like I said before, with an LRUCache, the underlying, you don't need that many methods for the underlying linked list, because whenever you set a value in your cache, you want to make whatever that value is to the front, so push front. Whenever you retrieve a value from the cache, you want to make the value, whichever value you retrieved, you want to move that to the front because now it's the most recently used. And then whenever you insert too many, so like the cache should have a fixed size, and so once you've inserted too many values into the cache, once you've exceeded your capacity, you should remove the tail node or the tail node. So in that case, what we could do is we actually call remove on the tail node. So yeah, that should work. And then, so actually, yeah, let's make one more test. I'm gonna make one more test for removing the tail node, so we'll make sure that works. We're gonna copy this test. Remove tail. So I'm gonna push two values to the front. Let's do this one. This is gonna be 02. And let's make this. What we're gonna do is assert equal. So we're gonna check what the current tail. We're gonna assert what the current tail is. So this current tail should be node 1 tail. But then once we do remove tail, so this also should be, we can assert this. So this should be 1, no 2. And then, so once we remove it, the length should be 1. And then we're gonna move this, and now since we're gonna remove, so node 1 is gonna be the tail initially, and once we remove the tail, the new tail is gonna be node 2. So we're gonna assert that. All right, let's try that. Perfect. Okay, so now removing the tail node does work. Give myself a little more. If anyone's curious, I'm drinking some peanut butter whiskey. I got this today because I've seen it before, and I thought it looked pretty cool. It is a little sweet, which is not my favorite. So I usually prefer, normal bourbons that aren't super sweet. But it's good for now. All right, so I feel like we have our linked list pretty much done. So now we can start working on the cache, which is actually the more fun part. And then from the cache, it tastes a little bit like whiskey with a hint of peanut butter, but it's a little on the sweeter side, which is like if it just tasted like peanut butter, I wouldn't mind. Like I would actually like that, but it tastes a little bit like it's kind of a sweeter. It has like sugar in it, which is the part I'm not a huge fan of. But like overall, it's kind of a dessert wine, or a dessert whiskey. So if you I don't know, have it after a meal or something like that, or after dinner, probably be good for that. All right. So yeah. So we got the linked list. So now let's actually try and make the cache. Where am I at right now? I can remove this test file. All right, so let's go out of here. And so now let's actually do the cache. So make sure my cabin's coming. Let's do cache, LRUCache. All right. There. Okay, so let's do LRUCache. So then the package name should not be main, it should be LRUCache. All right, so let's discuss this a little bit. So actually, let's also move this not from the small window, but from the big window. There we go. So the way that I imagine this LRUCache working is, you know, we have two main, so the API. So the API for a cache should just be basically set, so you're setting a value, and then get. And so set is going to be like a key value pair. So you're going to set like key value, and they're both going to be interfaces. Or actually, no, we'll make the key a string, just to make things easier. And then the value can be an interface. Value can be anything. Get is going to be the key, which is going to return the which is going to return the value. Yeah, interface. Okay. So simple API, but there's things happening under the hood. What I imagine that the actual cache should look like, so what the cache structure will look like is we're gonna have the linked list, which we created, the list, which is gonna basically, whenever we reach the max size, we can get rid of the last node. What we're also gonna do is we're gonna have basically a hash map structure. And so this hash map is going to be basically the key. So it's going to be basically a map with the key string. So this key that we pass in as the set value, we're going to have that be our key of our hash map. And it's going to point to a node in the linked list. So that way, whenever, that way, like, the reason we do that is because LRUCache should be fast. Whenever we retrieve a value, it should be O of 1 speed. So if we didn't have this hash map, we basically have to ask our linked list, hey, give me the value that has, or like, is there a node in this linked list that has this key value? And we basically have to iterate through our linked list to get the value. So it's going to be O of n time. So instead of doing that, we're going to have a hash map on the LRUCache, and it's going to tell us whether or not that value exists. And we can just pull it very fast. So that's gonna, so creating more memory with the hash map is gonna allow us to have faster speed of retrieval for the values. And then we're also going to have a max size. That way, like, we know if we hit our max size, we're gonna remove the tail of our linked list. The tail of the linked list is gonna be the least recently used. So that way we can expire that or remove it. So that way we always have a fixed size for our linked list. And the reason why you want to do that in real life is because, you know, say for example you have a Redis cache. If you say you're running like a virtual machine that only has like 1 GB of memory, you wouldn't want your Redis cache to grow exponentially, because if you like let it have free reign on your virtual machine, if you have a really popular app, like your Redis cache will get huge, bigger and bigger and bigger until the operating system essentially killed it. Because they say, oh, this application is running too much, has too much memory, we're gonna kill it, like out of memory, kill it. And so basically your Redis cache will go down. So by having a fixed size on the cache, whatever cache you're using, it prevents that from happening. So you can basically ensure that your cache will never go over a certain size. So that's kind of the practicality of having a least recently used cache, or at least a setting a max size to your cache. So yeah, that's gonna be the LRUCache. Yeah, let's try that out. So we're going to define our LRUCache. So as I mentioned, so the lists, we don't want to export that because we don't want people to access the list. So, but that's going to be the list from, that's going to be the list. That one, there we go. There we go. Make sure that it doesn't import the native one. Then we're also gonna have a map. So let's do okay. We're gonna have, I think we'll just call it like maybe items. That's gonna be a map of a string to list node. And then we're gonna have max size. And that's gonna be just an integer. All right. So what we're gonna do now is, oh, also what we need to do is we're gonna have a new method on here, and we're gonna pass in the size. So the user of this library can define the max size I want. So they're gonna pass, whenever they do new, they're gonna pass in the size, the max size of their cache. So what we're gonna do here is let's define a new value, and it's going to return a pointer to their LRUCache. And then they're gonna size it. So what we're gonna do here is going to do return LRUCache. So then max size equals the size. Items equals, we're just gonna make a new map structure. String, and then point to this node. And then what else we got? The list, linked list. That's gonna be list.new. Oh, what's happening? Modify level off. What is that? Oh, I need to, there we go. In Go, whenever you create like a structure, you have to always have commas at the end. I mean, it's kind of the same with like JSON and stuff. You have to always have the commas. And so if you don't have the commas, the compiler will throw warnings at you and be angry. All right, so new is gonna return this pointer to LRUCache. I have a lot of drinks in front of me. I have whiskey. I just finished my kombucha, and then I had some water as well. We'll be very hydrated. All right. Let's do the get method first. I think it's gonna be a little easier. So the get method, let's do this. Cache get, it's gonna be a key string. And it's going to return interface, just the interface value. And yeah, for anyone who doesn't know, interface in Go is just basically generic. It's like, it could be anything. You have to cast it to a certain type that you want. So what we're gonna do is first, we're gonna check if the item even exists. So node, okay. We're gonna do items. So we're checking to first, we're gonna check to see if the node is even there in our items list. So whenever you fetch an item from a map, you get the value back, but then you also get this OK value. What this OK value means is it's telling you whether or not the item was actually in the hash map. So for things like, sorry, for example, in like, I think it's JavaScript and Ruby, if you try and fetch something from a hash map and it doesn't exist, it'll give you like a nil value, which is nice, but it doesn't really tell you, or not, like, you know, maybe you actually set that value as nil, so it doesn't tell you whether or not that key was ever set. So in Go, the nice thing is that it actually will tell you if this key was ever set before. So we're gonna say if not, all right, instead of okay, let's do exists. That makes it a little more readable. So if it doesn't exist, what we're gonna do is just return nil, because what that means is it doesn't exist. Doesn't exist in our items. If it does exist, what should we do actually? So we should actually change this differently. That. So it doesn't exist, just return nil. If it does, so return value is going to be node value. So the thing about this, so with our lists, in our linked list, each node has a value, which is the interface. What we're gonna do is we're gonna set each value, or each node's value in our linked list as a structure in itself, and the structure is gonna be a key value pair. So we're gonna do, let's do type element. So what I mean by that is that, let's see if I can open it up. Oops. All right, so in our linked list, each value is an interface. What I'm saying is that for LRUCache, we're gonna set that value to be a key value pair, or a structure that has a key and value. So that way we can know. So basically what we're gonna do is whenever we create an item in our linked list, the item is gonna be like a structure. So it's gonna be, let's do element, maybe, just generic enough. Struct. And so it's gonna have this key, should be a string, and then value, which is gonna be interface. There we go. Cool. I'm actually thinking, do we even need to do we need this to be a node, or do we need this to be? No, it shouldn't be a node. It should be a node. Okay. So what we're gonna do here is it's gonna be elements or element, and we're gonna typecast this to be a pointer to the element. So because the value here is interface, we have to, interface is generic, so we have to cast it to the item that we want. In this case, it's going to be element with a key and value. And what we're going to do, and so then at the very end, what we're going to do is we're going to return element dot value, because that's going to be, in this case, it's going to be the value, like this interface value. But before we do that, since we fetched the value, or is it? Since we fetched a certain node, what that means is we want to move that node to the front of our linked list, so that way we know it's the most recently used node. Oops. We're gonna do. Oh, actually, we can make a cool thing is actually we can make that a defer statement. So if anyone doesn't know, defer is kind of a cool thing in Go, where you basically, what defer means is that a function that you define as a defer function, it will run when your function returns. So when this get method returns, it will run this defer because you're deferring it until the end. And so you can define something to always return at the end. So it's kind of nice, like if you have multiple conditionals, and regardless of the conditional, you have to have some logic run at the very end, you can have that run in a defer statement, which is kind of nice. So what I'm going to do is I'm going to do defer the list move front action, and we're going to have a node. And then, so this basically is a closure, because this node is referencing, this node right here is referencing this node we got up here. So it's basically a closure. Yeah. So let's try that. So we got node, it's gonna fetch it from the items, and we're gonna defer it to move to the front, and we're gonna turn value. Okay, let's make some tests. Test this out. Tests gets. Let's see, run get key. Let's do maybe get key from empty list, from empty cache. That way, just like our nil, like our base statement. So it's gonna return nil. All right, so, actually, yeah, we haven't defined our set method yet, so we can't actually put things into our cache yet, but we can do get. So we can do empty cache. So it should always return it should return nil. Let's do cache equals new. Let's do 10, or let's do 1. And then what we're gonna do is cache or value cache gets. Let's do key, pick key. And so then what we should do is save that, and we're going to start equal, and so t to equal, and then we're gonna make sure that we're gonna insert this value as nil. So it must be nil, and then it's gonna be value cast that as a nil, and so that should work. I guess we could just do also assert nil and value. Text interface. Yeah, it's text interface. Okay, cool. So let's try. So are we in LRUCache, right? Let's make a quick little. Actually, let's copy it from our list. We're just gonna copy a make file. Just gonna bat that to make sure. All right, have to test. All right, cool. So it works. So indeed, when we try and fetch a value from our list, it is empty. It's nil. All right, so that works. So now let's actually do set, because set will make things more interesting. Because now we'll be able to test whether or not we can, adding things to our cache. All right. LRUCache sets key is gonna be string, and then value is gonna be an interface. But set is definitely much more complicated. Actually no. Set is obviously much more complicated too. I think the return value of this should be maybe like so in case we eject something from our cache, I think maybe the return value of the set function should be if we eject something. So like if we reach our max size and we have to eject something, we return that. So in case anyone using this can do something with that value if it's been ejected out. Otherwise, if nothing's been booted out of the cache, we just return nil. So we can just return interface in that case. All right, so first things first, we're gonna do is create an element, which is gonna be element key value. Perfect. All right, and then afterwards, so create the element. We're gonna add that to our items list. Items key equals element. Oh wait, no. We don't do that. It's gonna be a node. So first we have to add it to our list. Push front, which is gonna be the element. It's gonna get a node back. So that gives us a node. Then we're gonna do list key equals node. That work? Oh no, items, sorry. Items. There we go. Now, so we add that to our node, we push to the front. We add it to our items list. Now we have to check if we're gonna check the list. We're gonna check the length of our list if it has exceeded our max size, we're going to boot out the tail of our list. So if list length is greater than max size, what we're going to do is we're going to do list remove list tail. And then, so what this should do, let's go back to our, so what this should do, actually when we do remove, we should return whatever node this is. I guess we don't have to, because technically we already have it. If we could do this. And then, so we're gonna do, actually let's do this, tail. Node. And then, so we can do this. So what I'm doing here is I'm defining the tail variable outside of this if conditional. The reason for that is because this if conditional creates its own scope. And so by declaring the tail out here, if we initialize it in here, then we can still reference it out of this if conditional. So that way I can do something like this, or I can do return tail value, something like that. But tail might be nil, so I have to way off of that. But yeah, so if I did do this, I just did tail here, I couldn't reference tail here. You can see it might see can undeclared name tail. If you look at this message down here, undeclared name tail. The reason for that is because I'm trying to access the tail outside of this if conditional block, so I can't do that. So I have to first initialize tail out here, and then that way I can reference it outside this block. So let's do this. What I actually might do instead, because so if I just do this, I'm just an empty node. I could do, okay, so I should be able to turn, even though this is going to be like, this is basically a nil list node, a nil structure should at least still have this value structure. Oh, we'll see. It might, if I try and access this value with it being nil, it'll return a panic. So don't have to worry about it. Okay, so now that we have a node, we're going to remove the tail. What we're going to do now is we're going to remove, so items, we're going to move this from the items as well. Remove node. Oh wait, no. How do I do this again? I think so. If you want to remove an item from a hash map, I think Go has a built-in remove method. So I'm gonna do items and then node. Is that not? All right, let me time for some. From Stack Overflow. Oh, is it delete? That was a remove. I guess it's delete. There we go. It's delete. Okay. So we're gonna delete this node from our items. Oh wait, no, it's the key. We can do. Let's see. We need to remove employee. Okay, so remove the key actually, so not the node. So we actually don't even need this this node here. So we can actually do, we could do key. So this is the key we get from the set method here. So we're gonna remove the key from our map, and so that way it's not gonna be there anymore. And then remove the from our tail. Yeah, that should be good. and we're going to return whatever item we booted. So if we didn't boot anything, this should be nil. If we did boot something, it should be this right here. And so we'll get it out. So let's try it. Let's do a test for that. So we have an empty map. So let's add one more test to our tested get here. So get key from non-empty map, or empty cache. So what we're gonna do cache sets, foo and bar. There we go. So then, oh, thanks for the follow, Crashbase. Hope you're enjoying the stream. Cheers. So what we're gonna do is we're going to get foo from here. Foo. And so let's see. Foo should now be, so we should get, so value should be bar in this case. And so if we do equal, and then what we're going to do is bar is expected. And so if we do value to type cast it to a string. All right, so we set something and then we are trying to get back that value. And so we want the value should equal what we expect this with bar in this case. So let's try testing that. Ooh, fall. That's always fun. All right, so let's look at this stack trace. So line 18, line 69 of our cache. Line 69. Okay, so we are getting, okay, that makes sense. So what it's saying is that we can't access this value field from a nil structure. So this, whenever we do like var, like this, basically this syntax right here, so var tail, we're initializing it as a nil structure. We can't access a field from a nil structure. So what we have to actually do instead is, what we're gonna do is tail equals new node. So what this does is we're actually initializing the structure, or this node. So we're actually going to initialize the structure, so that way we can actually access the value. The value is gonna be nil, but the difference between this and what we had before, var tail list node, I think, is that this is essentially nil. This is just nil. It's a nil pointer, where this is, I just comment that out. This is actually creating the structure, but it's like an empty structure. But we can still, in that case, we can access the value field. So let's try this instead. That should be better. Boom, got it. All right, my hunch is correct. All right. So that works. All right, so let's write some tests for a set. Set is more fun, to be honest. So func test sets testing at T. All right, so the first case should just be that when we set something in a cache that has space, because before I mentioned that if we set something to a cache and we haven't exceeded the max size, we should just return nil. But if we have exceeded that max size, we should return back the value of whatever we booted out. So the first case should be inserting to a cache where we have plenty of space. So the return value should be nil. So let's do that. sets value in cache with space. Scripted enough. Test T. All right. So what we're gonna do is we're gonna create our cache, as we always do. So new one, and then if we do, so the value is going to be cache sets. Let's do the same thing we did before, foo and bar. So now what we're gonna do is we're gonna assert nil. So we're asserting that this value is gonna be nil. That's gonna be a simple case. So let's try that. All right, so that works. Now what we're gonna do is we're gonna do set, so we're gonna do the same thing as here. So let's actually copy this over. But we're gonna set something twice. So since the max size is only 1, whatever the second value we set, that it's gonna boot out the first value. So set value in cache with no space. So we're gonna do this. Let's do. So we should still, actually, I don't need this. I'm not gonna get that. But, so we're gonna do Baz. Stop being weird, Vim. I don't know, back. So what we're gonna do now is, so now that since we set the cache max size 1, we've already started one value. If we start another value, we should kick out this this bar value. Yeah. So value in this case, so we're gonna do assert equal value. So it should be bar is the value. And then we're gonna get value here. That should be correct. So bar value. Cool. So let's try that out. Ooh, not cool. Oh, what did I return out? Oh, I think I returned out the elements. Oh, you're right. I did. I did not return the string. I returned the this whole element structure. So in that case, what I need to do is convert this. Oops. And so I need to convert this into. All right, let's make this easier myself. I don't want to. All right, we're gonna do if tail value equals nil, then just return nil. All right, now it should be a little easier. All right, so now what we're gonna do is tail value. We're gonna cast this to pointer to the element. So we're gonna cast it because we know that when we the node's value in the linked list is gonna be this pointer to an element, and we're gonna return back the value. And then I should do this. Does that work? I know it looks pretty janky, but it should work. Let's try that. All right, so it works. So returning back the returning back bar, which is what we did here. All right, cool. So our cache actually kind of works. I mean, it's very simple. Like, the cache itself is actually much simpler than the backing linked list, but yeah, it should work. Cool. All right, so now what I want to do is actually want to actually build something with this. So I've built up this LRUCache. I don't know, let's try building out some sort of like, I don't know, this could be like a data store for something. So I'm gonna create like a simple API. So I'm gonna use like a HTTP, basically create a server, have two HTTP endpoints, one for set, one for get, and then that way we can actually like use it as some sort of data store. We can use it for like the eventual goal is to use it for the dist cache, like white paper that I showed like much earlier. That's kind of like the eventual goal. Right now, I just want to actually try to make sure this works. One thing I haven't actually taken into account, for example, is like concurrency. If I have multiple Go routines that are accessing this this cache, I haven't tested out that multiple Go routines can do that. So that's one thing we can definitely check out, and we can test out. For example, yeah. So like for example, if I had 2 Go routines, both trying to set two different values. Actually, let's try that. Let's try that. I haven't made this thread safe, so let's try 2 different Go routines happening. Let's do multiple Go routines setting values. So what I'm gonna do, create this cache, and then I'm going to so I'm gonna do a loop. Each loop I'm going to, let's do so I can show off some group. So what I'm gonna do is basically do some concurrency, make a test with some concurrency. So what I'm gonna do here, let's do 2. All right, so what I'm gonna do is add 1, and what I'm gonna do is go func. So the reason why I'm doing this I equals I again is because since I is a shared value, we don't want to, or what we can do actually instead of doing that is I'm going to do this balance, and I'm going to do cache sets foo, and I'm gonna actually set it as the value here. So I'm gonna have, let's do multiple, let's do like 5. Let's do 5 Go routines. They're all gonna try and set the value foo for whatever I equals. So in Go, this Go syntax right here is basically you're creating a new thread that executes this function. So that's what here is. So we're gonna basically create 5 new threads. Well, each one has to do defer done. So we're each gonna try to set the value, and basically we're creating a race condition because we have 5 threads all trying to set this key to be a different value, and then what we want essentially is, actually I don't even know what we want. I don't even know what we want for this. I think the whole point is just to show that I'm not even totally sure what we want with this, but I don't know. Let's try it. If we do this, I'm sure it's gonna. If we do a test with a race flag, I'm sure it's gonna tell us we have a race condition. And I guess what we can insert is if we do get, maybe we want this to be 5. Value. All right. So let's try that. I'm sure it's gonna fail. Oops. Yeah, I'm sure that failed. Let's see. Yeah, concurrent map writes. That's exactly what happened. So then let's do file. Let's do this with a race flag. What that means is that it's going to check if there's any race conditions in our test. So taking a long time to run. Was it like a deadlock or something? What is happening there? Yep, we're in data race right here. So there is indeed a race condition. So what we can do there is we can actually use something called a mutex. So I actually learned about these a little more yesterday. So we're gonna add to this. What we're gonna add to this cache is a mutex essentially. And so what that means is that whenever we try and access a key in the mutex, it's going to lock. Basically lock that key, so only one go routine can access it at a time. So, let's do mutex. Sync read write mutex. All right. All right, man. See it. Thanks for stopping by. All right. Let's see. So what we're gonna do here, so it gets so we're gonna do is mutex rlock unlock. What this means basically is that we're locking it for reads. So since get is a read action, we're locking this for reads. And then, so we're basically whenever a go routine hits here, only one can access the cache at a time. And so what we're gonna do here is we're going to essentially, we're gonna do mutex lock. And then I guess defer unlock. All right, let's try that. Get food. Okay. Why? Expected 5. What it's saying is that this was actually int. Get foo. It's saying a set was here. Oh, you know what I need to do? I need to wait. Cause basically what's happening is that I split up all these go routines. I'm trying to set them to a certain value, but if I don't wait for the go routines to finish, what basically happens is I split up all these go routines, and then I immediately try and read from the cache. And so if the go routines haven't finished yet, then they haven't finished actually right into the cache. And so I'm going to try that now. Is nil not int? What the heck? What going on? Oh, now I see what happened. Oh, interesting. So basically what's happening is, okay. Basically what's happening is, every time I set foo, I'm actually creating a new element. I'm actually creating a new element, meaning that, what is it? So yeah, every time I create foo, I'm creating this new element, with a new value. So so what I was expecting to happen was I'm basically like setting a new value for foo every time. What I'm actually doing is I'm actually creating a new element every time. And so what happened was, when I do delete key, since foo is the only value in my list, basically my list is empty once I delete this line runs, because I'm deleting foo, and the only value in my list or my items map is foo. So what I need to do instead is I need to check if that value exists. So what I'm gonna do, we're gonna do, I'm actually gonna make this a helper function. We're gonna make this a small get function. Cache gets key string, and it's gonna return back a node, and there we go. All right. So we're gonna do node get small. Why is this? Oh, list node. There we go. All right. So what we're going to do is we're going to do the same thing here. So when we try and set a value, we're first going to see if there's already a node that exists with that value. If there is, so if node is not nil, so ideally if the key is new, node should be nil. If it is not nil, then we're going to do node value I cast this to the pointer to element. Value equals value, and then return value. Oh, return nil. That should work. And then, okay, so we have a guard case essentially. So if the key already exists, then we're just going to overwrite the previous value. Oh, we should create a lock on this. Oh, do I delete that? I just want to. All right. All right, let's see how that works. Where am I at? 67. Oh. Alright, what's happening now? Ooh, a seg faults. 46. Oh, gotcha. So I need to do equals nil, return nil. Positive sign. taking a longer run. Some spacing to make it easier to read. Alright, so it's running a little longer, so let's see how this goes. There's a good sign that's taking long. I think the reason why it's taking longer for this to run is that with the race flag, I think what it does is it spins up go routines in the background. It spins up multiple threads in the background to check if, like, you know, the test is thread safe. So let's see what happens when it returns. Alright. Wait 5 minutes longer, I might just cancel this. I think I'll run it without the race flag. 5, 4, 3, 2, 1. Alright. So instead, let's see. Maybe if I don't. Let's try it, run it without the race flag. Let's try it now. Come on. There's just like a... What's happening? Am I just not unlocking something? Let's go back. Alright, so that should unlock it. This should also unlock it. Oh, I get it. I know what happens. I don't unlock this. Okay, let's try that. So basically what's happening was I wasn't unlocking this write me text or read me text. So now this should... oh, there you go. Alright, so that should be better. I think we're just gonna... Alright, honestly, since we don't even know what this value should equal, we're just gonna do not nil. That should be the real test, because Go routines can finish in whatever time they want. So we can't really assert what this value should be. So we're just gonna do not nil. All right, so then let's do makefile. Let's add that race file back in. Test. Let's try this. All right, cool. All right, nice. All right, so I think for today it's good. Yeah. So essentially what happened was we were able to build our lists. we're able to build our LRUCache. So now we have a functioning LRUCache as thread safe for the most part. So yeah, I think we're actually pretty good. So yeah, I think that's enough for today. I saw this thing earlier where I actually raid somebody. I might want to try that. So let's try that. But yeah, thanks for joining me today, and yeah, have a fun time. Hope you learned some stuff. All right, talk to you guys later.